Hello, Steve.
Hello, Mr. Fox. How are you?
Not too bad, not too bad. Steve, you're going to start a bit of a show here, and I hope tell everybody what it is you've been doing for the last 3 or 4 years from ever spending all this money.
That's right. It's very important. I'll cover the project from east to west, showing its 4 main features. The new surface route.
Okay.
Then the short tunnel.
Yeah.
Then the long tunnel.
Okay.
And then the tunnel ventilation system.
Okay, that's great.
First, the surface route. About 15 kilometers from end to end, with its 4 culverts and 5 bridges over the major creeks.
What about the viaduct? You're going to do something on that viaduct, I hope.
Of course, the viaduct. We'll make sure they get a good look at that viaduct. Then we'll look at the short tunnel, the Mount Shaughnessy tunnel.
You're going to show them the benching operation, Steve, too, eh?
Right. Then we'll take a look at the long tunnel, the Mount Mcdonald tunnel. We'll go underground and see some of the work in progress.
You're going to take a look at the gate chamber and the air tunnels?
You bet. We'll explain the whole tunnel ventilation system, and we'll show the ventilation shaft.
Good. That's a key feature of the whole project.
And I'll point out the purpose of the project is to reduce the westbound grade from an average of 2.2% to 1% and to increase our westbound train capacity.
Okay, Steve, that sounds pretty good. You know, this is the largest project CP Rail's had in the last 100 years. As a matter of fact, since we built the railway initially. And, you know, we want everyone to know what a project is all about and all the facts of it. So, you know, go get it and let's get it done.
Okay, I'm on my way.
Fine.
The Rogers Pass project began in 1984, and it'll be completed in late 1988. The cost is about $600 million. We're here at Cupola Creek Bridge, the beginning of the Rogers Pass project. From here, the grade reduction is from an average of 2.2% to 1%. The new line travels 34 kilometers up the Beaver Valley and under Rogers Pass. This reduction will increase westbound capacity from an average of 15 trains today to 24 trains per day, and that's important to CP Rail. Here, less than 1 kilometer from Cupola Creek, we can see the old main line above and the new main line below as the grade reduction begins to take effect. Before we get to the end of the surface route, these tracks will be about 150 meters apart vertically. When the project is completed, the old line will handle only eastbound trains on its 2% downhill grade. The new line will handle westbound trains on its 1% grade. Even the heaviest 100-car trains will be able to take the new grade without having to add extra locomotives, which we call pusher locomotives. This will help CP Rail reduce costs, and it adds efficiency to its railway operations.
The new line uses the most modern track laying technology. Long lengths of 136-pound continuous welded steel rails are laid on concrete ties. Instead of the old familiar spikes used on wooden ties, the rails are fastened to the ties with these new clips. This is the first extensive use of concrete ties on CP Rail. They are expected to last for 40 years and will considerably reduce maintenance costs. Alder Creek here has the first of 4 culverts along the surface route. Each culvert is designed specifically to handle the different conditions of each creek. This one, for instance, is the only non-concrete culvert and the only one to have a bypass to handle the spring runoff. When the project is finished, the average track speed on this new line will be about 48 kilometers. This is twice as fast as we're going now, and considerably more than the present average of 19 kilometers per hour on the old line. Here, you can see how close we are to the Beaver River. Because of this, the old line had to be moved back into the rock about 10 meters to make room for the new line below. You can also see how far the grade reduction has now separated the two lines. This is Mountain Creek Bridge, the second of 5 bridges on the surface route. We are now about 4 kilometers west of Cupola Creek.
And we're approximately 40 meters below the old line. The bridge has 2 spans, each weighing about 250 tons.
These spans are the heaviest used on the entire surface route. Mountain Creek was one of the most difficult bridges to build because the center span was in the middle of the stream, and a specially lined dike had to be built around it to prevent muddying the water during construction.
Just ahead is another problem that had to be solved. The new line goes through a rock cut, one of the largest on the project.
And just to our left, behind the rock cut, is the Mountain Creek Campground. The campground had to be protected from the noise of the trains going by, so a huge noise berm is being built along this area. It will take 60,000 cubic meters of material and is expected to be a very effective noise barrier for the campground. Work on the surface route can be done only from May to October, and a lot is accomplished in that time. Only a year ago, many areas of the surface route were still under construction. And after that work was finished, the newly graded slopes were hydroseeded with a mixture of fertilizer, grass, and legume seeds. About 30,000 pounds of seeds and 100,000 pounds of fertilizer will be used on the project. And many of the 600,000 trees have already been planted. Today, the reclamation of the new surface route is well underway. But monitoring will continue after the project is complete to ensure that the reclamation standards of CP Rail and Parks Canada are fulfilled. This is Cedar Creek Culvert, the first of 3 concrete box culverts on the surface route. You can see the pattern of concrete arresters that is common to these culverts. The purpose of the arresters is to slow the flow of water and debris coming down the creek.
And now I want to give you a quick look at what this next section looked like just a year ago.
Then, when we go on, we'll be able to see how much has been accomplished in just 6 months working time. Because, don't forget, winter stops all work in this area. And now you can see the difference a few months has made. CP Rail engineers have taken great care to eliminate as many major curves as possible on the new line. Maximum curvature on the new surface route is 6 degrees, compared to more than 11 degrees on the old line. This is Raspberry Creek with its concrete box culvert, the second of 3 on the surface route. Each of these culverts has been designed to handle a maximum volume of runoff calculated for each creek.
We're now nearly 9 kilometers from the beginning of the project back at Cupola Creek. This is Gully Bridge, built over a dry gully.
Last year, Gully Bridge, like all the bridges on the surface route, was given a waterproofing treatment before the track was laid. And as you can see, Mr. Fox was a hands-on project director. He was then, and he still is.
These slopes ahead are some of the steepest on the project.
Because the slopes are so steep, they have to be held in place by retaining walls. You can see the top of a retaining wall here. There are 3 different types of these walls. The Type 1 retaining wall is made of shotcrete blown over a wire mesh, with pipes inserted for drainage. The Type 2 wall is also built of shotcrete over a wire mesh, but it has the additional reinforcement of steel rods anchored back into the rock from the rows of buttons you see along the wall. Type 1 and 2 walls are always built on the upper slopes of the new line. On the lower slopes, the more substantial Type 3 retaining walls are built. These are constructed of rows of precast vertical soldier piles erected on concrete footings. Steel rods anchor the soldier piles into the ground for more support. And the remainder of the walls are built of precast concrete panels. On the surface route, there will be about 26,000 square meters of retaining walls reinforcing the slopes, and some of them will be more than 10 meters high. This is the beginning of Wakely Siding, named for the former senior engineer of the Rogers Pass project. The siding can handle a train 200 cars long. We are now crossing Surprise Creek, the 3rd and last concrete box culvert on the surface route. Here we are about 10 kilometers from the beginning of the project, and we are the equivalent of a 22-story building below the old main line. We are now approaching the end of Wakely Siding. The train you see here carries the steel spans for the viaduct, which is not far ahead. Each span is about 30 meters long and takes more than 1 flat car to hold it. To get here, the train had to be detoured south through the Crow's Nest Pass because the long spans couldn't be accommodated on the curves and tunnels of the main line.
As the spans are needed on the viaduct, the cars are uncoupled and pushed across Stony Creek Bridge.
This work has been going on for several weeks. The viaduct spans are offloaded here from their flat cars and hauled by truck to the viaduct site about 1/2 kilometer ahead. Each span weighs about 90 tons. Here is a wider view of the offloading site of the viaduct spans at Stony Creek. And you get a good look at Stony Creek Bridge, the longest at 211 meters and the highest bridge on the surface route. We are now 13 kilometers from the beginning of the project and 146 meters, or the equivalent of a 40-story building, lower than the old line. As we proceed toward the viaduct, you will see that the slopes in this area are very steep, most of them 40 degrees or more. Because of this slope, the retaining walls are longer and higher here than anywhere else on the surface route. And because we are in Glacier National Park, we have to work in a right-of-way that is only 30 meters wide. These steep slopes and narrow right-of-way are the reason for building the viaduct in this section. The usual cut and fill method that we saw back beyond Stony Creek can't be used in this confined space. The solution to this problem is a series of piers, 44 of them, forming a viaduct more than a kilometer long, a unique feature of the surface route. Because the terrain is so varied, each pier had to be specifically designed for its particular location. Mr. Fox claims that the viaduct is the greatest engineering feat on the whole Rogers Pass project. This is the beginning of the viaduct. The spans, each 30 meters long, were launched from pier to pier, starting at this point. And on top of them, the new rail line will be laid. A special launching machine was built to put the viaduct spans in place. The truck we saw earlier backs the spans along the completed viaduct to the launcher. And the launcher projects each span out from one pier to the next and lowers it into place. Then the launcher advances along the newly laid span and repeats the operation on the next pier. This process continues until all 45 spans have been laid and the 1,229-meter road bed across the viaduct is complete. We are now approaching the end of the viaduct. Ahead you see its final abutment. And on the right is the east portal of the Mount Shaughnessy Tunnel, the second major feature on the Rogers Pass project. The Mount Shaughnessy Tunnel is a short tunnel, 1.8 kilometers long. But when it is finished, 88,000 cubic meters of earth and rock will have been removed from it. Just a year ago, the tunnel looked like this, with the portal just beginning to take shape. Now the portal is finished and the tunnel is broken through. The walls and arch are reinforced with steel. And benching operations to finish the bottom part of the tunnel are now being done. At the other end, the west portal of the Mount Shaughnessy Tunnel there is another short section of the surface route. It crosses the fifth and last bridge of the project over Connaught Creek. A feature of this 1.5 kilometer section of surface route is the bear pit. The bear pit is a huge depression that is being filled with tunnel muck from both the Mount Shaughnessy and the Mount Mcdonald tunnels. Filling the bear pit has been going on for more than 2 years, and about 400,000 cubic meters of material has been used. We are now approaching the east portal of the long tunnel, the Mount Mcdonald Tunnel. This tunnel is more than 14 kilometers long, the longest railway tunnel in North America, and it is the third major feature of the Rogers Pass project. On the left, you can see the agitator cars and a computer-controlled batching plant for the concrete work now going on inside the tunnel.
How you doing?
Not bad.
How's it going?
It's going great. We're just about to go in the tunnel.
Well, stay away from that bench. They're ready to blast in there.
Okay, will do.
Okay, fine.
This is the east portal of the Mount Mcdonald Tunnel. The Mount Mcdonald Tunnel was cut from each end using entirely different methods. From the east portal, the tunnel was cut in this round form by a cutting machine known as the mole. Last year, the mole's work was finished. But the tunnel was still incomplete. The lower half, about 3 meters deep, had to be cut out. The shaping operation of the lower half of the tunnel is called benching, and benching is proceeding now, almost 5 kilometers into the mountain. When benching is completed, the tunnel lining begins. On the east side of the tunnel, the first step in lining is to build these 2.5 meter high sidewalls called pony walls. And the next step is to complete the sides and the arch of the tunnel. In October of 1986, the tunnel work from each end met near the halfway point of the tunnel. Mr. Russell Allison, president of CP Rail, set off the final blast, and the tunnel was through from end to end. Now, near the point of the breakthrough, a huge chamber, 25 meters high, has been cut to straddle the tunnel. This chamber will house the center automatic gate for the tunnel ventilation system. Then, about 50 meters on either side of the gate chamber, a smaller air tunnel has been cut, which leads to the bottom of the ventilation shaft. The ventilation shaft is 8.5 meters in diameter, and it goes straight up 350 meters from the tunnel level to the top of the mountain. The ventilation system employs unique engineering concepts, and will be the only one of its kind in the Western Hemisphere. The purpose of the ventilation system is to cool the tunnel and clear the air of exhaust fumes from passing trains. This is done by a complex of fans, automatic doors, and the division of the vertical shaft into two. As a train approaches the tunnel from the east, the portal door automatically opens to allow it to enter, but a door in the center of the tunnel remains closed. Air is taken in and forced along the tunnel against the direction of the train, providing a cooling flow of air and taking the exhaust gases with it out the eastern end. As the train nears the center of the tunnel, the door there automatically opens to allow it through, and the air is drawn from the western portal to continue the cooling and purging process. The center door automatically closes after the train passes, but the flow of air goes on. This system purges gases from the tunnel much faster than they could otherwise be, and trains can pass through at intervals of about 35 minutes. This may seem like a long time between trains, but a unit coal train with more than 100 cars will take about 30 minutes to pass through the tunnel. So you can see that the operation will be very efficient. When the tunnel is finished, at least 9 or 10 more westbound trains per day will be able to use the line. Not far from the installations for the ventilation system, work is proceeding on the sub-invert of the tunnel. The sub-invert is the base on which the final roadbed or pack track will be laid. It contains drains to take care of water seepage in the tunnel. The west side of the tunnel employed an entirely different construction system from the cutting method of the mole on the east side. Here, the tunnel was drilled and blasted out in its final shape. Then, when drilling and blasting was completed, a 30-meter-long mobile machine completely lined the side walls and arch with concrete in one operation. This gives you a good idea of what the finished tunnel will look like. The tracks you see are a temporary narrow gauge line for the work trains. The finished tunnel will be 5.2 meters wide and almost 8 meters high from rail to arch. And it will be lighted from end to end. And this is the west portal of the Mount Mcdonald Tunnel. We are now more than 14 kilometers from the east portal of the tunnel and 34 kilometers from the beginning of the Rogers Pass project at Cupola Creek.
And that's the Rogers Pass project. Basically, it's a grade reduction project designed to increase railway capacity westbound. It covers 34 kilometers up the Beaver Valley and under Rogers Pass in Glacier National Park, BC. It has 4 main features: an 18-kilometer surface route, a 1.8-kilometer short tunnel, a 14-kilometer long tunnel, and a sophisticated tunnel ventilation system. When the project is finished in 1988, CP Rail's capacity for westbound trains will be assured for the foreseeable future.
Hi, Steve.
Hello, Mr. Fox.
How'd it go?
It went great. We went from the eastern portion of the project right through to the western end of the project.
Good.
Well, people were really impressed with that surface route, and the viaduct in particular.
Okay, that's great.
That viaduct, that's about the most important engineering feat on the project, isn't it?
Well, not necessarily the most important, but certainly one of the more difficult parts of the project.
People really were intrigued by the slopes.
Oh, that's great. How about bears? See any bears?
Not a one, not a one.
Our luck is not with us today.
Oh,